Hello everyone, welcome back to the channel. In today's tutorial, we are going to learn how to perform supervised land use and land cover classification using Google Earth Engine and the random forest machine learning algorithm that is necessary. So let's begin by exploring the complete workflow shown on the this image. So here is the first step, and this first step is defining the region of interest, commonly called the ROI. So this is the area where we want to perform land cover classification. The ROI limits our analysis to only the selected region, reducing the computation time and ensuring that only relevant satellite images are processed. And next we have a Sentinel-2 image collection. So this next step is collecting Sentinel-2 imagery. Like we use the Sentinel-2 surface reflectance harmonized dataset available in Google Earth Engine. So what Sentinel to provide is a very high spatial resolution, that is from 10 meter to 60 meter. We have 13 multispectral bands. We have frequent revisit time of Sentinel, and it's free global coverage. We filter the image based on the study area date and the cloud percentage. And then we have the third step. It's a raw image often contain clouds and multiple acquisitions. So therefore, pre-processing is required before classification. In this step, we will remove the cloudy pixels, we will create a cloud-free median composite, and we will create a clip uh, of the image for our study area. So this is the third step that involve the image pre-processing. Then we have the spectral feature extraction. So instead of using only spectral bands, we improve the classification by calculating additional spectral indices. So in this workflow, we calculate four important indices. So the first one is NDVI. The NDVI is Normalized Difference Vegetation Index. NDVI highlights healthy vegetation. Higher NDVI values usually indicate dense vegetation. Then we have NDBI, the build-up index. So normalized reference build-up index. This is what it stands for. And NDBI enhances urban and built-up areas. And then we have MNDWI. It is a modified normalized reference water index. So MNDWI improve water body detection while suppressing built-up land. It is particularly useful for the lakes and the rivers. And then we have BSI, the bare soil index. BSA actually highlights exposed soil, barren land, and rocky surfaces. So this helps to distinguish between bare land from vegetation. So these indices provide additional information that improve the performance of the machine learning classifier. Okay, the next step is the most important step where we take the ground control points, GCPs, the training samples, the most important step in supervised classification. So here we manually create the training samples. Uh, for every land cover class, we have a separate training sample. Unlike unsupervised classification, supervised classification required labeled examples. Each point or polygon represent a non-land cover type. So this is how this step will work. For example, we will take water, glacier, forest, agriculture, vegetation, built up area, and barren land. For all of these classes, we'll have separate training samples for each class. So the quality of these training samples largely determine the quality of the final classification. So the final results depends on the training samples. If you take the training samples really good, your final LULC TIFF will be really good. And then we have training dataset generation. So what is it? Once training samples are collected, Google Earth Engine extract the pixels values beneath every sample, and these values include spectral bands and spectral indices. Together, they create a feature table like that. This feature table becomes the training dataset used by the random forest. So if we say it in a simple words, the machine learning model learned the spectral characteristics of each land cover class from these training samples. So this is how it's worked. And then we have land cover classification. Okay, now the random forest classifier analyze every pixel in the satellite image. For every pixel, it compares its spectral values with the learned pattern from the training data. So the algorithm then predicts the most likely land cover class. The result is the final classified land use land cover map like that. And then we have the accuracy assessment, the step 9. Producing a classified map is not enough in supervised classification. We also need to evaluate how accurate it is. So this is done using a validation data. So here is the training data and here is the validation data. Several statistical measures are calculated, uh, and these statistical measures are overall accuracy, producer's accuracy, user accuracy, kappa coefficient, F1 score, and confusion matrix like that. So these matrices help determine how the reliable classification is. If you don't understand this, comment below. I'll make a detailed video on accuracy assessment and the random forest classifier. And then we have the export results. Uh, Finally, the classified map and the related outputs are exported. These outputs may include GeoTIFF classifier raster, CSV accuracy, report, GeoJSON training samples. These files can be used in ArcGIS Pro, QGIS, or other GIS software for further analysis. So this is how you can do supervised classification, land use land cover classification using Sentinel-2, using the spectral indices, using the random forest machine learning and accuracy assessment. So now let's get back to the code and discuss the dataset that we're going to use. So we're going to use Copernicus harmonized Sentinel-2 dataset. Let's discuss it a little bit. Okay, now let's understand the dataset used in this project. The primary dataset is Sentinel-2 surface reflectance harmonized, and the dataset contain atmospherically corrected Sentinel-2 imagery because it's Sentinel. Surface reflectance means atmospherically effect such as aerosols and gases have already been corrected, making the reflectance values more reliable for land cover classification. So Sentinel-2 provide multiple spectral bands and making the reflectance values more reliable for land cover classification. So Sentinel-2 provide multiple spectral bands. Among these, we have a lot of bands over here, and from these bands, we can calculate several indices like NDVI for vegetation, NDBI for urban areas, MNDWI for water, BSI for bare soil index. So these additional features insignificantly improve the classification performance of the random forest algorithm. And now let's get back to the code and let's discuss the code. Okay, now let's start to discuss the code line by line. So first of all, what I'm gonna do is to import my shapefile. So I'm gonna use Lahore shapefile for my study area. So here is my shapefile. Let's import it and rename it as ROI. So the first line adds our region of interest or ROI to the map, and this allows us to visualize the study area boundary. So the empty curly brackets over here is indicate that we are using the default display setting, and Potohar is simply the layer name shown in the layers panel. So we can change it from Potohar to Lahore or any of the study area you are using. And next we just center the map to on our study area using map.center object. So here ROI represents the study area while 8 is the zoom level, the only change in the map view and does not affect the analysis. Okay, so now we load the Sentinel Surface 2 Reflectance Harmonized dataset. So this is an image collection, meaning it contains thousands of Sentinel 2 images captured over different dataset. The surface reflecting product has already been automatically corrected and make it more suitable for land cover classification. And then we have just applied the filter for the date, like the date that we're gonna use. So I am using from 2020 to 2021. Then I have applied the filter to just restrict it to just my study area, not for the any other. This filter keep only the images that intersect our region of interest. Instead of processing global imagery, Earth Engine retrieve only the images covering the Potohar Plateau. And then we have the pre-filter to get the less cloudy granules. So what will it do? It will remove the high cloudy images. Like the LT, the less than function means less than. So the only images with the less than 20% cloud cover are selected, and this improves the quality of the final composite. And then we're going to select a band, and we select all the sentinel-2 spectral bands. So expression uh, B dot is a regular expression that matches every band beginning with the letter B, such as band 2, band 3, band 4, band 11, and band 12. And then we have created the median composite over here. Like, now we create a median composite from all the filtered images. The median over here is a function that calculates the median value for each pixel across the entire image collection, so helping remove residual clouds and noise. After that, we have applied the clip, trim the image so that only the study area remains. And then now we're gonna add the indices for our study area. So we have created a variable add indice, and we have defined a function image. So we define a custom function called add indices. This function calculates several spectral indices that provide additional information about vegetation, water, urban areas, and bare soil. And next we have added the NDVI. As already discussed, this line will calculate the normalized difference vegetation index, or NDVI. It used the near infrared band, band 8, and the red band, band 4. Healthy vegetation reflect more near infrared light and absorb red light, resulting is higher NDVI values. Then we have NDBI, and here we calculate the normalized difference build-up index. It uses the short-wave infrared and near infrared band to highlight built-up and urban areas, making it easier to distinguish cities from vegetation. Then we have MNDWI. This line calculates the modified normalized difference water index. It uses green band and shortwave infrared 1 band to enhance the water bodies while stressing up built-up land and vegetation. And next we have the most important, the bare soil index. So the bare soil index cannot be calculated using simple normalized difference function. So we use image expression rather than using a simple formula for that. Okay, so this is the mathematical formula used to calculate the bare soil index. So it compares the reflectance of shortwave infrared and red bands against near infrared and blue bands. Then we have the X image dot select band 11. X represent the shortwave 1 band, and which is sensitive to soil moisture and bare land. We have band 4. Y represent the red band, and here A represent the near infrared band and B represent the blue band, and we have renamed it as BSI. And after doing all of that, we just, instead of replacing the original spectral band, we add 4 new indices as additional bands. The final image now contains both the original sentinel-2 bands and the newly calculated spectral indices, providing richer information for the random forest classifier. So here we added all of the bands into the map. And then we have some of the visualization parameters. This line simply crosses the custom function here. And then we have visualization. Next, we define the visualization parameter for displaying the satellite image, and we have just added it into the map. What we added, the composite, this one, the visualization parameters, here is it, and the Potohar image clip. We can say it Lahore. And now let's run the code. Okay, now just take the training samples. I have run the code and added all of the indices into the map. So for now, let's take the first for the uh, water index. So for that, let's do this. And you can see that water is not really clear. So we can just stretch it from custom to 90% and apply. Okay, as you can see it's same, so apply it again. Okay, now water is clear, so we can take the training samples in the water. So click on here and go to the setting, name it as water, and click here, feature collection, property, capital C, and class. We will start it from 0 and okay. Okay, now just zoom in and take just off this and take the training samples into the water. Uh, Now let's take the point for built up areas. Just rename it as build up and feature collection, property, class, and here you can say it 1. Now just activate build up index. Stretch it to 90% and apply. Okay, so these are the reddish areas where we have a lot of build up. So let's take the point in the reddish areas, and you can confirm it by showing the true color image. Close it, and we have now the true color image and the NDBI. So let's confirm it and take the points. Okay, so here is, you can see these all are the build-ups. So now let's take this and okay. So now it's confirmed that these reddish areas is a build-up. Now let's untick it and take the points over here. You can just take the random point starting from here to onward. So the sample region function extract pixel values from the satellite image at the location of our training samples. So we have given it collection GCPs. So this tells the Earth engine to use our ground control points. And then we have properties. So the copies the land cover attribute from each training samples. This attribute represent the correct class label such as water, forest buildup, and then we have the scale of 10 because we are using Sentinel 2, which have 10 spatial resolution of 10 meter. So we're going to use this, and then we have this prints the extracted training dataset. Each row represent one training sample, while the column contains spectral bands, spectral indices, and the corresponding land cover labels. And then we have a train the classifier. So now we create the random forest classifier. So we have created a variable classifier. So what it means, the value of 50 means that the algorithm will build 50 decision trees, and random forest combine the prediction of many trees to improve classification accuracy and reduce outfitting. And this specifies the training data set. This tells the classifier which column contain the correct class labels. And this tells the classifier, this last line, to use all the spectral bands and spectral indices available in the composite image as predictor variables. So this is all about the train a classifier. Then we will classify the image. We have created a variable var classified composite dot classify classifier. So now now the trained random forest model predict the land cover class for every pixel in the satellite image. So this is how it works. Then we have some of the visualization parameters. The palette, we define a color palette for visualizing the classified map. Each color corresponds to a different land cover class. For example, pink for the buildup, and yellow for the barren land, blue for the water, dark green for the vegetation, and so on. And then we have added this into the map. We display the classified land cover map. The image is clipped to the study area and the color palette is applied to visualize each class. And the next step is the most important. We have the accuracy assessment. So we have created a variable, um, new GCP dot random column. So to evaluate our model, we first randomly assign every ground control point to a random value between 0 and 1. So these random values is later used to split the dataset into training and validation samples. Then we have created a variable training GCP. So this select approximately 60% uh, of the ground control points for the training. And then we have validation GCPs. This will select the 40% points for the validation. These validation samples are never used during training, allowing us to evaluate the classifier on independent data. And then we have just print the training GCP and print the validation GCP sizes. These lines display the number of training and the validation samples in the console. Okay, now we'll use the GCP, which is 154 as the training sample, and keep 140 overlap training point is the image to get the training data. Okay, now we train again using only the training samples. We have created a variable training. So now we'll repeat the sampling process actually. But this time we use only the training ground control points. We are using the scale of 16, and then we have created a variable classifier. Now we are again doing the classifying. So we have created a variable classifier. We train new random forest model using only the trained datasets. So we have another variable classified. Now we classify the completely image using the newly trained model. And we have then the visualization palette I already discussed. We are adding it to the map and clipped it to the ROI, print the validation GCPs, and then we have to test the simple regions. So now we extract the predicted class values at the validation sample locations. This create a comparison between the non-land cover labels and the predicted labels. And then we have confusion matrix. This over here. This line create the confusion matrix. The confusion matrix compares the actual land cover class with the predicted class. It forms the basics of the calculating all the classification accuracy statistics. And then we have print the confusion matrix. We have printed the accuracy, overall accuracy. Over here we have the accuracy, and then we have also user accuracy, consumer accuracy, producer accuracy, kappa coefficient, and F score. Okay, so kappa measures the agreement between the classified map and the reference data while accounting for agreement that cloud cover by chance. A kappa value close to 1 indicate excellent agreement, and where values close to 0 indicate poor agreement. So if the kappa coefficient is greater than 0.6, it's good. If it's greater than 0.8, it's really good. And if it's greater than 0.7, it means that the accuracy is moderate. That 0.8 is considered as a good. So F1 score, then we have printed the F1 score. What is it? It is especially useful when evaluating the performance of individual land cover classes, particularly when the class distribution is unbalanced. And then we just export the training samples. Um, this export the region of interest of the training data to Google Drive in GeoJSON format, or maybe we can use it in the future. And then we just export the image into the drive. We are using the export image to drive. We are using image classified clip image. We have the description, you can change it. We have the folder in the drive, region of interest, scale, file format, and pixel, max pixel values. Okay, so what you need to change is you can see that we have the water buildup and vegetation, right? And we have the region of interest. So what you need to change is you can come over here. The Okay, here I was talking about this. So what you need to do is to change this and rename it as our first class. You can check your class name from here, the first, and merge with, we have second class buildup, and we have third class of vegetation. And now just delete all the other classes. Okay, here is the code settled down. Now let's run the code and see the results. If you get something errors like missing property land cover, you can just rename it as to class, because we gave it a property name as a class. So just rename it. Okay, so here you can see our classified imagery, which have the built-up area, the vegetation, and the water, the simplest classes that we can extract from any of the study area. So this is the water, and this is the built-up areas. Here is also some water, the water, the built-up areas, and the vegetation. Inside the vegetation, we have the agriculture, we have the simple vegetation. So it's just mixed up over here. You can also take different classes for that. So this was our classification. You can also export the Potohar shapefile, its accuracy, LULC Potohar, and classified image to Drive, and then you can use it in your any of the GIS software.